Swayam Prabha. Digital India. Educated India.
So this application example, as you can see on your screen already, it has a composite beam made of two different materials. So you see the top part is material 1, which is wood over here, and in the bottom you have a smallish steel plate which is of 12 thickness over here, and the wood, the height of the wood is 150 What you are also given are the modulus of elasticity, and now you know why you are given this, because you have to calculate the modular ratio n, right? And what the problem asks you is to find that given this beam is subjected to a 6 kilonewton meter bending moment, positive bending moment, so sagging, right? Now you have to have a bending moment to have stresses, otherwise you will not have stresses. So for a positive bending moment of 6 kilonewton meter, what is the maximum and the minimum stresses in the wood? Now we can roughly tell the maximum and the minimum is compression. So if it's a sagging, so the top part will be in compression, and this part, this interface over here, will be in tension, where we'll have the maximum stresses. And similar for the steel. So for the steel, as you can tell, if this is the neutral axis over here, so in this if I just go ahead and say that this is my neutral axis, so along that particular line and below that, the whole beam will be in tension. So both the maximum and the minimum stresses in steel will be in tension over here, right? So let's maybe reiterate and take a look at the problem. So you are essentially given a beam like this over here. So say the top part is wood and the bottom part is steel, right? So now you are given that I'm just reiterating the problem, just trying to imagine it with the beam that I have over here, and then you are giving a positive bending. Positive means sagging, so it is sagging like this. So as you can see that the top part is in compression and the bottom part is in tension, and the neutral axis is somewhere over here. Now the neutral axis, you cannot from the problem example that you see, the neutral axis you cannot simply find by taking from this composite section, because the neutral axis is not going to coincide with the centroid of the composite section that you have. It coincides with the centroid of the transformed section, as we had seen, right? So now let's go ahead and try to do this problem. So remember that the first step of our using the method of transformed sections to solve composite beams is to calculate the modular ratio. So here the problem, what we're going to do before we start punching in the numbers, is that we are going to take this beam. It is made of partly of wood and partly of steel. We are going to transform this beam to a beam which is made of one single material. There are two ways to do it. You can either transform the wood to the steel, or you can transform the steel to the wood. So typically what I prefer doing is that transforming the stiffer material to the less stiff. So essentially you have a widening. So here what I'm going to do, I'm going to transform the steel to the wood. So what you expect to see is the bottom part to be widened. Remember, the height always stays the same because the strain profile stays unchanged. Or if you want to transform the wood to the steel, what you will essentially have, that this wood and this particular width is going to shrink. So you are going to have a T kind of a beam. So you will have this one over here and a small shrunk out portion of the wood now converted to steel. So let's go ahead using the first transformation, that we are converting the steel to the wood. So for that we have to calculate, remember, first is the modular ratio. So let us calculate the modular ratio over here. So I'm going to write the modular ratio. N is simply E2 divided by E1 over here. So that is 210 divided by 10.5. So now if you calculate this one, what you essentially get is 20, right? So my modular ratio N is 20. So I have calculated my modular ratio over here. So now how am I going to use this modular ratio? Remember, the second or the third step is that the width of the material 2 now increases. So the material 1 stays the same. So material 1, the section that you see over here, it stays the same. Only for the material 2 the width increases. So let me go ahead and put the picture here for material 2. Now this whole problem is from one of your textbooks, the Gear and Goodness. So if you want, you can take a look at that as well. So let me now go ahead and paste the picture of the transformed section. That is here. Now I have the transformed section. So you see in the transformed section, so the entirety is made of material 1. So here you had material 1, material 2, and I've converted material 2 to material 1. So as you can tell that what was that initial width of 100 mm over here. So now that width, so what was B initially? So what was your B initially? It now becomes, you know, n times B over here, because you're increasing the width over here. So that means that what was initially my 100 mm for the steel plate, now I've converted to material 1, and the equivalent width is going to be n times 100. So that is 20 times 100. So that is, you know, 2000 mm, or essentially 20 meters, which is your this part over here. So your top part stays intact. Top part 100 by 150 made of material 1, it stays intact. Only the bottom part over here, where the width which was 100 mm, now it has been bumped up to n times 100. That is sorry, this is not 20 meters, this is 2 meters over here. It has been bumped up to 2 meters over here. So you have a 2 meter thing over here. So now the entire section is now made of material 1. As you can see in the diagram here, it was material 1, material 2 here. Now the entire section is made of material 1. Okay, so now that we have a transformed section where the entire section is made of one single material, we can go ahead and, you know, apply our basic principles that now the neutral axis must coincide with the centroidal axis. So that means that I have to find my location of the centroid. So this is the neutral axis which was there in the beam. So this is also now coincides with the centroidal axis that is there. So for that, these are the heights which are given. So this is the height h1 from the top to the centroid. So this is also my centroid now for the transformed section. Remember, it's not the centroid of the original section, it is the centroid for the transformed section. So let me also mark that one over here. So this is my centroid. Let me just write this centroid, as well as this is my, you know, neutral axis over here, right? So for this we have to calculate the h1 and the h2 for the transform section, which is fairly simple, and I'm not going to write out the different equations for that. You just have to, you know, take the moments of the areas about the bottom or at the top or wherever you want to take to calculate h1 and h2. The h1 and h2 I've computed already. Now another thing that you would need, remember, to calculate your sigma is the formula sigma equals my by I. So you have to calculate the area moment of inertia also about the centroidal axis or about the neutral axis for the transformed section, right, which you can also easily calculate. You have, you know, these two separate rectangular chunks. You calculate the area moment of inertia of these individual chunks, and then you apply the parallel axis theorem to compute about the neutral axis. So I'm going to write out the final numbers that we get over here. So what we get, your h1, what we get is h1 comes out to be 124.8 mm. Your h2 comes out to be 37. I have this solved already, or you can take a look at the textbook, the Gear and Goodno, which is there. And then the I of the transformed section, remember, for the transform, not for the original one, the I for the transformed section comes out as 89 times 10 raised to 6 mm raised to 4. So I have the basic properties of the basic material set. Now let's me go ahead and try to solve this first part over here, which asks is the maximum and the minimum stresses in the wood. So the maximum, and then I know that the minimum stress means the compressive stresses, which is the negative stress that I have. And for this one, remember that I have, you know, the top part is the wood, so the compressive minimum stress or the compressive is going to happen at the top over here. So that is fairly, you know, straightforward to calculate. So let me, so that I know, so the minimum stress in the wood, it occurs at A, right, at this particular point over here, right, and the maximum is going to happen here because the wood ends at this point C. So it's a maximum tensile stress at C. So the maximum is going to happen at C, right? Now what about for the steel? The steel will be entirety in tension because it is below the neutral axis over here. So the bottom part is the steel. You see the steel is entirety in tension. So the minimum tensile stress, of course, will occur at this interface over here. So it is going to happen at C, and the maximum you know, tensile stress is going to happen at this, the bottommost interface. So that is at B over here. So let's go ahead and calculate that. What I'm going to write over here is that for wood, right, I'm going to have your sigma 1, which is the one representing the material 1 at A, where the minimum stresses occur over here, is going to be equal to what. So now I know it is compressive already, so I'm just going, so don't be bogged down by the signs, it is compressive. I'm just putting a negative over here. It's going to be minus m times this height over here, this is h1 by I, my by I. Simply I've applied the I for the transform section, so that is easy to calculate. Your moment is given as 6 kilonewton meters over here, so it is going to be 6 into 10 raised to 6 times h1 I've calculated, it is 124.8 divided by the I of the transform section, that is 89 into 10 raised to 6. So that will, the number that it will give you is, sorry, I forgot the negative sign, it will be minus 8.42 MPa, right? Similarly, so this is the minimum stress that you have over here, and the maximum stress is going to happen at this interface C over here. So sigma 1 at C will be similarly 6 into 10 raised to 6. It will positive now because it's tensile, times, you know, this distance from here to here. So that is going to be h2 minus this 12 mm that we see, because we are not altering the height, remember. So it is going to be 37.2 minus, because we calculated h2 as 37.2, minus 12 divided by the I of the transform section, which is 89 into 10 raised to 6, and this one you get as 1.69 MPa. So this is for the wood, right? So for the wood, now we have computed this is the minimum and this is the maximum. Now next is for the steel. Now remember, in the method of transform sections, what we do is that we calculate the stresses for material 1 at wherever we need to compute, right, wherever it encompasses the material 2, and then we multiply with the modular ratio n. So for steel, so let's just calculate for steel, right? So for steel, it is going to be what? For steel, the minimum stress occurs at this point C over here. So let's just calculate that. So this is going to be sigma 2, because I'm calculating for material 2 at C, is going to be what? Is going to be equal to sigma 1 at C times the modular ratio n. Simple, because the stress for this one, remember, is that linear variation that I have, and this is the interface where I expect the jump. So this is the interface C, which is shared both by the wood and the steel, right? So here I'm going to calculate sigma 1 times sigma 1 for the material 1 at C, and I'm going to multiply with the modular ratio. So that is nothing but your 1.69, which I have already calculated over here, times your 20. So that comes out as 34 MPa. Right? And lastly, it asks for the maximum stress. So the maximum stress, or the maximum tensile stress, in this case, it happens at this interface B over here. That is your sigma 2 B will be equal to what? Similar to what we saw, is going to be sigma 1 at B. Although originally the material 1 does not occur at B, but we have now transformed the material 1 to material 2 to entirely consist of material 1 and material, the entirety is in material 1. So I can, for this material 1, which is wood, I can calculate the one at B over here, and I simply have to multiply with the modular ratio n. So sigma 1 at B times n. So I need to calculate this first part over here because I have not calculated it earlier. So it is going to be what? It is going to be 6 into 10 raised to 6 times this height, the whole height h2 now. So that is 37.2. So I'm just simply going to write h2. You can substitute and calculate, divided by the I of the transformed section, times 20. Don't forget that. So that comes out to be around 50.2 MPa. So here for the steel, so this is the minimum and this is the maximum. Now remember that for steel both are tensile, so this is both are tensile, so good to make a note. whereas for here this is, you know, compressive, and this is tensile. So I hope this problem was clear, that how we, you know, took this entire material made of, you know, material 1 and 2 and converted to that one, but we back calculate to find the stresses using this modular ratio that we have over here. Remember, at the onset of when we started talking about composite beams, we said one of the classic examples of composite beams are everything, all the structures around you, all the reinforced concrete beams that you see are composite beams, because it consists of two dissimilar materials, concrete, and the second one is steel over here. So this is a, you know, one of the examples where different materials which come together and essentially help you to build all the structures around you. Now if you think of composite beam, so this is a reinforced concrete beam that you have over here, right? You will see that typically that if you see in this beam, your moment is acting like this over here, right? So that means that the bottom part of the beam is in tension, right? So now concrete as a material is very weak in tension, and that is the sole reason why you provide steel within the concrete structures to take the tension, because concrete by itself cannot take the tension. When you will take a course in structural design in your next semester, or maybe a couple of semesters from now, you will learn more about the properties of concrete and the properties of steel, and why steel is absolutely essential to take care of the tension that is there, right? Now here in this beam also you will have a neutral axis somewhere, right? Now what is typically assumed, and this I am saying over and over, and you will hear this a lot more when you take the concrete design, is that when you have a beam that is made of reinforced concrete and you have a neutral axis somewhere within the section, you have a neutral axis, because of this moment you will have a top is in compression and the bottom part is in tension. You'll have a neutral axis over here. Below the neutral axis, concrete is actually so weak in tension. Below the neutral axis, it is assumed that concrete does not contribute at all to taking the stress due to the tensile stresses which might occur in the beam, right? So the entirety of the tensile stress is assumed to be taken by the steel reinforcements that you have over here. Now again, since it's a composite beam, you're talking about two materials, steel maybe with a modulus velocity E2, concrete with a modulus velocity E1, right? And as is, you know, sort of conventional, and like the way we saw in the previous example, we convert the more stiffer material into the less stiffer material. So essentially you're converting the whole beam into one single material, right? Now since the concrete is not taking any tension, its concrete is going to be cracked over here, the composite section or the transformed section for this one looks a little funny. So this looks something like this over here, where above the here, so we are essentially converting the steel, right, into this n times AST that you have over here. So this AST that you see over here, so let me just, you know, mark it. So the AST that we see is, so this one is the area of steel, right? And n, as you know, is the modular ratio. So this n, so this one AST is this guy over here, and this n is nothing but the modular ratio, which is nothing but equals to your n equals to the E of steel divided by the E of concrete, right? So what you have done over here, you have transformed the whole material that you see over here into one single material, that is concrete, the top part. Now when you convert, whatever was the original material, whatever part of the beam was the original material, stays the same, which is what you have over here. So above the neutral axis, concrete stays as concrete, but below the neutral axis, since you're assuming that concrete is cracked, so essentially there is no concrete, or it does not help in anything in reducing carrying the tension. All the tension is taken by the steel, but now you have to convert the steel into the corresponding material one, that is concrete. So you multiply the area of the steel, the total area that you have, with n, the modular ratio. So that essentially gives you the spread of, you know, this entire area over here. Now this method of solving reinforced concrete beams and essentially designing, so see, the whole point of designing is that you're trying to find that to resist a particular tension, how much amount of steel do I need? Do I need 3 bars, 4 bars, or, you know, I don't know what is the grade of steel that you need, right? So this method of designing beams used to be a very integral part of what was known previously as the working stress method. Now In the latest code, this has been revised. We have moved on to the ultimate design method, which you will learn a lot more in your concrete design class. So this method is a little bit obsolete because the working stress method is no longer in existence, but I just wanted you to be aware that there was a time when the reinforced concrete beams were also solved using the similar principles of the method of transformed sections. So the next topic which we are going to explore is something which is very intuitive and something which you already have been exposed to. These are beams under bending, but also at the same time they have some axial load acting within the beam. Now, as we had seen before, that for these kinds of beams, what we need to do is that we have the bending stresses due to the very nature that of the bending action itself, and in addition to that, we need to add or subtract the axial stresses which is caused by the axial load. So let's go ahead and take a look into that, and after which we'll solve a problem example. Essentially, you're looking at beams with axial loading, and as you can see from here itself, so this is something which is quite obvious. So if you have a beam where if you have a load which is acting, you can replace the load with an equivalent load, right? We're acting at the centroid and a particular moment depending upon the eccentricity. Now this is one of the cases where you can have a beam with axial loading which also causes a moment. The other cases can be that you have the beam where a moment is already being applied, and on top of that you're applying another axial load. So let's go ahead and take a look at some of such examples which can occur in in structure. So okay, so this is the easiest to understand and the simplest and the classic case, the most classic case that you have. So here you see you have a beam which is, and now we are done with composite sections. We are now going back to beams which have the material is homogeneous across the entire length and the width of the beam that is there, right? So now for the beam that you have, so I am applying a sagging kind of a moment, something like this over here. Now in addition to that, there is an axial load. So essentially it's an action which is happening something like this, right? So as a consequence of this, if we take a look at the stresses, how do the stresses look like, or how do the stresses vary? Let's see. Now due to this bending moment M, or so this is the overall stress distribution that you have. So this is due to the axial load. So this is maybe we can write this is due to the P that you have over here, right? This is P divided by A. Now you see here the P acts exactly at the centroid, and what we had seen in our chapter on axial loading is that when P acts at the centroid, that means the stress distribution must be uniform across the cross section, and that is what you see over here. So stress distribution is uniform, right? Now this is due to the P, and this is due to the pure bending M, because you have an M and M. So you have this this phenomenon of pure bending where across the length of the member the bending moment doesn't change. So this is due to the M that we have over here. Now as you can imagine, since so this is like the method of superposition where you're taking the moment and looking at it separately, taking the axial load and looking at it separately. Once you combine them, this is the joint stress distribution that you have. Now as you see that here the load P that you had applied was tensile, so the tensile arrows have increased in length and the compressive arrows have decreased in length. So this can be one of the cases where your entire section does not have any amount of compression. It's completely under tension over here. Now as you can rightly say that of course it depends upon the magnitude of P that you have over here. For example, you can have a case like this as well. So you have the same due to P and you have due to M over here, but again depending upon the magnitude, maybe you are not able to nullify all of the compressive forces. Maybe you have a large amount of tensile force at the bottom, and depending upon how much of these tensile force did you have due to the pulling action due to the axial load, you can have the combined loading something like this. So you can have a very tiny amount of compressive load at the top and large amount of tensile loads at the bottom, and in between, as you can understand, the neutral axis will shift, right? Now the neutral axis, remember, the neutral axis coincides with the centroid only in the case of the pure bending, and that too when the material is homogeneous throughout. Now by the very definition, the neutral axis is the axis about which you do not have any stress or you do not have any strain, or for that matter any deformation. So as you see in this figure over here, this is the point where you do not have any stress or any particular strain. So the neutral axis, which was initially at the center over here, it now shifts under the action of this combined loading where you have bending as well as the axial loading. Right now, one important thing to note over here is that this stress over here is uniform throughout. Why? Because P, it acts as the centroid. So here maybe we make a quick note that here it acts at centroid, right? So since it acts at the centroid, you're having, you know, this sigma x as a uniform distribution. Now for this particular case, what we just saw, if we now just have to write our sigma, if we just go back to the previous slide, so here remember that what we are used to writing, that our sigma x is essentially your P divided by A for this one, and for this one we had seen that our sigma x is equal to minus of my by I. Again, don't be too bogged down with the signs and everything. Try to have a, you know, logical, sorry, let me just rewrite that slightly below. It overlapped with my camera. So here sigma x equals to minus my by I. Again, don't be bogged down with the signs and everything. Always make a logical judgment about the sign. So all I'm saying is that once we have this load, so once you combine the effects of both the bending as well as the axial, you can write your sigma x equals to P divided by A minus my by I over here. Right, so this is the overall symbol. So as you see, the top part which is in compression and the bottom part is in tension, that since the P is here is tensile, so this is positive over here, and this is what we had derived. So this is positive. This turns out to be positive when you have a tensile, because you are taking the y from the neutral axis below, so negative and negative becomes positive. For the, you know the drill, you have already done this. Okay, now, so this was the case where P acts exactly at the centroid of the cross section. Now you may have a case that, so this is the case where you have the moment and the P acts exactly at the centroid of the cross section. Now what happens if it acts as an eccentricity? You can guess it already. Essentially what you do in this case, so this is the case where you have this moment M over here and you have this load P, but then this load P, now it acts at a certain eccentricity E over here. So as you can understand, what you have to do here, you have to shift this point of action of this load P from here to the centroid. Now because of, after shifting the load P to the centroid, you will have a uniform stress distribution, but in addition to shifting the load P, you have to add a moment, that is P times E, that is there. So essentially at that particular point you have a net moment which is M, you know, minus P, that is there, and you have that axial force that is acting. So it overall it looks something like this. So you have this beam, you have this M and M over here, and this is the load P which is acting at this eccentricity E. You are going ahead and shifting this load P from here to the centroid, this P over here, and as a consequence of that, take a look at the sign. You are going from this P to here, so you are having a clockwise kind of a moment. So P times this moment arm, that is E, so you're going on a clockwise moment, so you have a clockwise direction. So that gives the result of your clockwise moment in this direction and the anti-clockwise in this direction, because to balance you have to have the P in this particular direction over here, right? So now that you have this one, how is the formula going to change? Let's we have already seen what the formula is because of this P and this because of this M in the previous page. So let's just write the revised formula is going to be P divided by A minus of M Y divided by I. Now in addition to that, I have this clockwise moment, you know, this is over here. So for that, the moment arm for that is P times E, and the arm from the neutral axis is still going to be the same, that is Y divided by I over here. This part is the additional moment. So I hope this is clear, and it is very intuitive. Once you understand axial loading by itself, you understand bending by itself, it's easily a piece of cake to put these two together and to look at systems which are subjected to the joint action of the bending as well as the axial load. Now with this understanding, and again, do not be bogged down by the signs. have a logical interpretation of the problem. Compression is typically negative, tension is typically positive. So find out those individual stresses and then you decide that whether you want to attach a positive or a negative sign to that. So we will look at one particular example problem will specifically deals with that, and will reinforce the ideas which we studied in this particular. So the example that you see over here is that you have a cast iron chain link, which is this one over here. So there are too many things in the figure, so let's just go step by step. So this cast iron chain link that you see, it has these two holes across which you're applying this force F over here. So F and F over here, right? And the line of action say coincides with this point D over here, which is a random section where you have taken somewhere in between. Now what it says, now you can already imagine that how this is going to sort of go down. So if you're not applying the forces exactly at the centroid, this is going to bend into something like this over here, right? Now as a result of applying this load, what you have are the different stresses and strains which are going to happen. Now let's see what the problem says. The problem says that the allowable stress in tension, right, is 30 MPa. Now you can understand that the tension is going to happen at the the top that you have over here, right, and the compression is going to happen at the bottom, right? And the largest allowable the stress in compression is 120 MPa. What you're asked, since you're as typical of this problem, since you're given the allowable loads, you're asked to find what is the largest force that you can apply so that these allowable stresses in either tension or compression are not exceeded. Now let's see what we are given in the problem. What you're given is of course the chain link that is there, and at any particular section XX. So if you take a section somewhere, and if you're looking at this section, this is the cross section of the member. So this is essentially, see the first figure, it shows this. So if you're taking a cross section somewhere, it shows you how the cross section looks like. So in the cross section you have these points again, that is P and Q, the top and the bottom. And the dimensions are given 20 mm, 40 mm over here, and this is the line of action of this point of this force D. So the D is falls along the line of action of this force F over here, right, which is also over here. So you are applying this here. If you're taking this section, if you're cutting the beam at this particular along PQ over here, this is how you see it's going to happen over it, and the total height is 60, and so this total height also must be 60. Now let's see what are some of the additional informations that are given. You are given the area of cross section of this this section that you see, that is 3000 mm square, or 3 into 10 raised to minus 3 meter square, and you're also given the area moment of inertia. All are given in terms of meters. Okay, and also one more thing which is already given, but you can easily calculate, you are expected to calculate this actually, is that what is the location of the center. So now it is too much down the line that we have come to go back and calculate the centroids and all. So this is given, but you should be in a position to compute that. So C in this section, see here you have this P, Q and D over here. C is not there. C is essentially the centroid of the cross section. So let's maybe make a note of that. So C is nothing but the centroid. So you have the centroid of this section, and the centroid is at a distance of 22 mm from the top. After you calculate the centroid, this is the distances you will get. You might calculate it to double check. And from the bottom is 30. It's a total 60 that you have. What's the total height of the section is 60 mm. Right? Okay, now how do we approach this problem? So as you can understand, so we have this force F, which is an eccentric load that you have. So we have to shift this force F to the centroid. And why do we have to shift it? To get a uniform axial stress distribution. Now as a consequence of the shifting, we also have to have for an equivalent force distribution, we also have to add a couple over here, or a moment over here, right? So let's draw the equivalent section for this one. So the equivalent section for this one maybe something like this, So here again I have my points P and Q over here. I have my point D where the force was originally acting, and this is my centroid C over here. But here now I am going to apply the force F. I have transferred to that particular point. Now in addition to the force, I have to have a moment. Now what will be the direction of the moment? You can see from here as well, again plain intuition, the direction of the moment will be clockwise along above both the, so it is going to rotate, you're going to sag your beam, right? So this F times D, this is the moment arm. So if you do, it's a clockwise moment that you are having over here. So it is going to have, this is the moment M, which is nothing but equals to F times D. Now what is D? D is the eccentricity over here. D can be easily calculated. You see this distance that you have, it is already given from the bottom to the top, that is Q to D, it is given as 10 mm. So this is, let's just mark that over here. So this is 10 mm. So your distance D will be 38 minus 10, that is 28 mm. So equals to 28 mm. Since everything is given in meters, I'm going to write in meters. So it is going to be 0.028 F over here. Okay, so we have calculated D and we have calculated the force over here. So let's make a note over here. D equals to 28 mm. Okay, so now what are we going to have? We are going to have, due to this force F that you see, this force F is going to cause a uniform stress distribution, and this will cause bending stresses. Now, how we know already how to compute those things. So maybe let's draw the overall stress distribution, if I may. That so let's just first draw the uniform stress distribution that is there. So that is going to be, so that is due to F. So let's just write it F over here. So due to F, I am going to get F divided by A, that is the area of cross section. So this is nothing but F divided by A, and the other one, the bending, so this is due to F, and I'm going to have the one for the M here as well. So let me draw another cross section. So this is due to your M. So M, since it is acting clockwise over here, as you can understand that the bottom part will be in compression and the top part will be in tension. So, and your centroid is, somewhere about, say, this particular point. It's not exactly at the center. It cannot exactly be at the center because it's not a proper rectangle. So it will be slightly, in this case, slightly shifted up over here. But the stress distribution will be something like this. So as we interpreted, the bottom is in compression. Okay, so you are going to have to add these two because it's a combined loading case that you have over here. Now after adding that, what is going to be my resultant stress distribution? The resultant stress distribution is going to be, so you see these compressive forces are going to add up, and some part of the tensile force will be, and it depends upon the values that you get, but as a generic representation, so this was my C over here. I forgot to note that. So this point was my C over here, right? So here my point C is over here, right? But now in the combined case, the neutral axis will be shifted. So it will no longer be at C. So it is going to be maybe somewhere here, right? So you will have a larger, maybe if I exaggerate this a bit more, because you see these compressions are going to add up. So you're going to have a higher compressive force at the bottom. So it may be the higher compressive stress at the bottom. So it may be, something maybe quite dramatic as like this. So you have a larger compressive stresses and maybe a tiny amount of tension. It of course depends upon the magnitude of the forces and so on that you get, but this is the equivalent one that you have. So we are trying to find this one, right? We are going to add these two and try to find it, because, and why are we adding? Because we individually know how this is, so we are going to add it and find that what is the the top one will be tensile, right? What is the tensile force you have at the top and what is the compressive force you have at the bottom? So here is tensile. I'll just indicate this explicitly. So it is compressive. Right. So here, so let us write the overall tensile stress that is there. So if I have to write, so this is sigma, say, T, and this is sigma, say, C over here. So let me write the expression for the sigma T first. So sigma T that I get is going to be the sigma T due to the moment, right? And then I'm going to have to, you know, add this guy over here. Now since this is compression, this is where you again take the logical symbols and everything. So since this is the compressive force, the tensile, I have marked it as a positive, so I have not attached a negative sign over here, it is positive. So so this tensile is positive, and then in addition to that I have to attach this one, and this is a negative sign because it's compressive. So this is again logically what you do over here. So F divided by A. Now if you plug in the numbers, what you essentially get here, that your sigma tensile out of the moment, it comes out as what? It is going to be your this guy over here, that is your 0. So sorry, I should scroll and show this one, this moment over here. So 0.028 F, 0.028 F times, this is going to be this particular distance from C to above, so that is 22 mm, times 0.022, because initially I am writing everything in meters, so I'm just going to write it the same, divided by the I which is given over here. So this is the I which we have. So now, so this is the part for this guy over here. Now minus, we have F divided by A, so that is minus F divided by the area of cross section, which is this one over here. So F divided by 3 into 10 raised to minus 3. Now if you combine these two guys over here, the number that you will you know, eventually get is that you will get, this is the tension part, so you will get 377 F. So this is the overall tension force that you're getting, positive, right? So if you plug in the numbers, you will see this F and this I. So overall it comes out as positive. That means that even after the application of the load, you still have a tiny amount of, you know, tensile force over here. Now let's go ahead and write the bottom part for this one, this compressive force. So we will get your sigma C will be simply the addition of these two over here, and I'm going to write both with a negative sign. So I'm going to have minus of essentially a similar quantity, so minus sigma C comma M minus F divided by A. Now if you again plug in the numbers, what you will get is that, so here this one was this guy over here, so I'm writing that first time, I'm writing this one now, is going to be 0.028 F times the arm for the compression, that is the base, that is the 38 mm. So times 0.038 divided by I minus this, it remains the same because it's the uniform compression that you have. And if you plug this in, what you're going to get for here is going to be minus of 1559 F. Right? So overall you see that we have now gotten, you know, two expressions, one for the tensile force and the other one is for the compressive force that you have. Now we are already given the allowable loads which are there, and one of them is going to control. So we are going to simply have to equate. So the allowable stress in tension is 30 and allowable stress in compression is 120 over here. So we simply have to equate this 377 F. This is the tensile, so we have to equate that to this one over here. So equating the allowable stresses, so let's just, you know, make a note of it and write it down. So equating allowable stresses, what you essentially get is 377 F is equal to 30, and the next one minus 1559 F is going to be for the compression, right? So that is 120, so it's minus 120 because it's compressive over here, right? So if you do both of these things, what you will essentially get is that the first one, that is when you equate to the 30 over here, this one will give you your F as 79.6 kilonewton, and you have to of course convert, you know, the units and all, because here remember that while deriving this we have taken this in meters and all, but here this is 30 MPa, so it is Newton per mm square. So be careful with the units when you're working with these problems. And the bottom one, F, is going to be 77 kilonewton. So as you can understand, this is the controlling F. So this is the largest Right? So this is very easy to interpret once you understand the overall logic that how to do this problem. These are quite easy to interpret. So essentially you take the force and you shift the force to the centroid. In addition to that, you add the consequent moment that you have, and then you logically figure out where is going to be compression and what is going to be tension. You add the things with the proper signs and all after making these logical deductions. Now this problem can be made even more complex by, in addition to this F, if we apply an external bending moment over there. So in that case, you will boil down to the stresses due to the applied bending moment, the stresses due to this F that is here when you shift to the centroid, and after shifting to the centroid, this is essentially this FD that you see over here. So this, so this is the maximum these problems can be, this maximum complexity these problems can essentially have. So do a few practice problems on your own to reinforce some of these concepts. Last small topic that we have left in our chapter on pure bending is an extremely interesting topic, and this is related to unsymmetric bending. That is that when your bending moment is acting about an arbitrary axis. Now before going into looking at some of the formulations for that, let me ask you a question. Now the beam bendings which we have looked at, right? So something like this over here. Now you see that the face, the section, say it has two axes. Say this is the ZZ axis and this is the vertical axis is the YY axis, the horizontal is the ZZ axis over here. Now when we considered when we calculated the sigma x, when the beam was bending like this over here, right? So when the beam bends like this, essentially this beam is bending about this ZZ axis over here. So the formulation that we do, that sigma x equals to my by I, that I is actually the IZZ, because it is bending about it is bending about this particular axis that you see over here, right? It is bending like this. Now instead of bending like this, what if the beam was bending like this? When the beam is bending like this over here, right, that time the bending is about the YY axis, right? So when it is bending like this, it is about the ZZ. When it is bending like this, it is about the YY axis that is bending. So now if the beam, instead of our traditionally how we are used to seeing, instead of the beam bending like this over here, where you calculate sigma x equals to my by IZZ, if the beam was bending like this, right? So if you're looking from the top, it's like this. If you're bending by like this, then in that case your sigma x becomes m divided by IYY, because it is bending about this axis over here. Okay, now let's go ahead and see that in addition to the moment acting about or bending happening about this axis or about this axis over here, if it happens about any arbitrary axis, how do we find the stresses? How do we locate the neutral axis? That is the main point of this particular topic that is there, right? So unsymmetric bending. So as you can see from the figure here itself, and I'm sure that this pokes your mind into thinking something about resolving of forces, moments, and so on, and it's exactly what it is. So what you see over here is that you have the moment which is acting about this axis. Now so this is something like this over here. So instead of like this or like this, maybe your beam is bending about about a particular angle over here, so which is neither perpendicular to this nor perpendicular to this, but maybe at a particular angle you're trying to twist it over here. Yeah, so again going back, so this is how it acts. Now don't be confused by these double arrows. So the moments like couples, torques can also be represented by these double arrows. All it means is that your thumb points towards that. So it's essentially something like this over here. So the moment I'm bending like this, that means my moment is pointing towards that. So this double arrow, so if I am supposed to represent the moment in terms of a straight line instead of the curved arrow we see always, it is this this one, a straight line along this with a double arrow, straight line along where my thumb is pointing with a double arrow. That means that I'm trying to bend about this axis over here, and about that arbitrary axis I'm talking about. So this is what you see over here, that this moment is acting like that. Now you see this is your ZZ axis over here and this is your YY axis. So essentially what you are doing here in this case is that you're resolving, and suppose this angle at which this moment is acting, the arbitrary angle, say it makes an angle of theta, with the horizontal. This is the theta that you see over here. So this moment can be resolved like we do like we resolve forces. The moments can also be resolved into a moment along the y-axis over here. So this moment will rotate the element vertically, and you have another moment over here, that is the mz, right? So this moment now I have resolved it. So now that I have resolved it, so with these individual moments, now my problem is more or less simple. Now I have resolved the the inclined moment into a moment along this and a moment along this over here. So that part is resolved. Now, although that part is resolved, how do I locate the neutral axis? Which is the axis, or is there an axis at all about which the stresses are zero? Let's go ahead and take a look into that. Right. So if we just move ahead and just to give you an example, so this is what it is. This is what we were talking about. This moment m, which is acting at an angle of theta over here. What I have done is that this is now resolved. Let me bring up my pen. So this is now resolved about about your mz. So if this is theta, this is m sine theta, and the other one is m cosine of theta over here. Now with these I have resolved the moments, right? Now let's see how the section maybe looks like. So suppose if I give you a general, so this is what it is. Suppose it's a prismatic section. The one which I was showing you with the styrofoam is a rectangular section, but as you know that the formulations we have derived are valid for any prismatic section. So now if I have this moment, see this is the symbol for the moment. The moment is acting about this particular line over here. Again, this arrow over here is the thumb, where the thumb point, you're curling this arrow points towards your thumb, and this is the way your fingers are curling over it. So various different ways of representing moments in different books. So you can have this one over here, you can have the double arrow, you can have a straight line with a position showing where the finger is curling. But anyway, you get the idea. So this is where your moment is acting, and you have resolved it along the mz and my. So mz is m cosine of theta, and my is m sine of theta over here. Okay, now let's look at these bits individually. So for the first one, so this is the mz over here, which is acting like this. And why is it acting like this? You may ask. Mz is pointing towards that. Now follow the arrow and the the curved line over here. Over here it is pointing like this, right? It is pointing like this. So that means that if this is my zz axis, this guy over here on the screen, it is marked like this with the finger curling. So fingers is curling like this. So that means my beam is bending like this over here, right? The beam is bending like this. My finger is curling like here, right? So this is how the moment is acting, m of z. Now for this one, we already know that this is our formula over here. We have looked at it, but now explicitly I am mentioning this iz because this is bending about the zz axis over here. Now be a bit careful about the symbols, although in the end it is not important. If you are balancing, if you are managing logically in your mind what is positive or what is compression, what is tension, but here it logically checks out. If you see, if I take a point on the top over here at this particular point at a distance y, what do I expect when the beam is bending like this? The top is in compression and the bottom is in tension. So if you put a positive y, because it is points along the positive y direction, positive y, if you put it here, it will come out as compression over here. Fine. Now that deals with the mz. Now let's deal with the other one, that is your my. So my also, you see from this figure over here, my finger is curling like this. So my is along like this. My is acting like this over it. It's bending the beam in plane like that, right? So now if you're talking about my, what should sigma x depend upon? Sigma x. So for this one over here the distance was about the y. Here the distance will be about z. So look at the same point. When I'm bending like this, what do I expect this point to be? This particular point to be in tension. So this essentially brings out that positive. So your m, when you write the sigma x, it should be a positive quantity over here. So if you write that, it comes out at something like this. Now note, very important to note, here it was bending about the zz axis, this axis over here. So you have a mzy by izz. Here it is bending about the y axis, so this axis. So that's why in the denominator you have iy over here. Now, but although you have split the moment into two moments, one about the z, one about the y axis over here, you are calculating the stresses at a particular point. So essentially the total stress at this particular point must be a summation of this stress and this stress over here, because I have resolved this moment into this and this, And for the same point, so this is again boils down to the principle of superposition. So for the individual ones I'm computing, and then I'm finally going to add it up. So if I add it up over here, this is what I get. So this is important. So here what it says is that for a point, right, in your beam, this is how we are going to calculate the moment. Now again, don't be too bogged down by the signs. If you're given a problem on unsymmetric sections, then just understand that what you have to do, you have to keep a logical track of where is going to be compression, where is going to be tension, and you subsequently add it up, you subtract. But anyway, this formulation, but that is not to say this formulation is incorrect. This is sign wise, it's a correct formulation what is there. Okay, so I have now kind of figured out that where or rather what the value of the stress is going to be at the different points. Now the question is that how do I find where the neutral axis is? Or now can you again think of what is the neutral axis? We always talk about neutral axis, sometimes get lost in conversation. Neutral axis, always remember, is the point where your strains are 0, stresses are 0, deformations are 0, right? So in all of this, there must be a line or somewhere where your sigma x must be 0. So how do I find that? So we know that the sigma x equals to 0 about the neutral. See, this is what it is. So this is the moment. Again, it is pointing towards a random direction, which is over here, and it is acting at an angle theta. Since it is acting at an angle theta, that's why in the previous slide we could resolve it into the cosine of theta and the sine of theta. That is there. But this is the neutral axis. The neutral axis is the axis about which your sigma x will be equals to 0. Now we have already derived the formula for sigma x over here. So if I just go and substitute that one over here, you will see that this boils down to something like this over here. If you put mz, remember this my which we had calculated. Let me just take you back to that page. My which we had calculated was m of sine of theta, and this was m of cosine of theta. So if you just come back and put it over here, this is m sine of theta, mz is m cosine of theta, and if you sort of dumb it down, you get this expression that y equals to this one. Now remember the equation of the straight line, that y equals to mx plus z, right? We all know that, where that m, right? So this is the sort of the expression that y equals to mz plus some constant c, where here this is 0 over here, right? So this m is essentially the slope. So this formula over here gives you the slope of the line about which your sigma x is 0, right? So this essentially gives you the slope of what? It essentially gives you the slope of the neutral axis of of the case where we have unsymmetric bending. So this is what it says. So this m that you see over here, so tangent of phi is essentially this particular quantity that you see over here. So this is the phi, essentially this guy over here where the neutral axis passes through, right? So although your moment is acting at an angle theta, remember the neutral axis need not be coinciding where the moment is acting. Neutral axis happens somewhere else at an angle phi, which can be calculated from the properties of the section, that is the Iy and the Iz and the angle where the moment is acting. So again, as I said, that signs are not important here, because you see here that this is this guy over here. It does not depend upon your stress is negative or positive. You keep a logical track of the stresses in your mind. This one is a flat out number which is dependent upon the area moment of inertia about the z-axis, area moment of inertia about the y-axis, and the tangent of theta, where theta is the angle about which the moment is acting. So I hope that this gives you some idea, although most of the problems that you will face as a structural engineer will be symmetric bending, where you will have either about the zz, about the yy, but you can have beams, you can have sections which are inclined at an angle where you have the unsymmetric bending case. And in that case, now after this this particular discussion, this small bit of discussion that we had, now you know that how to compute the moments, about how to resolve the moments, how to calculate the stresses, and most importantly, where is your neutral axis.